All right, welcome to part 2 of our video here. I should have just kept it on the same video, but hit the wrong button, so we know how that goes. Anyway, so for part 2, we're going to start talking about membrane transport, or how our cell is able to get solutes or things such as ions, proteins, sugars across its membrane. Okay, and there's two ways. Well, that's a lie. There's more than two ways, but the first thing we're going to talk about essentially what is needed to move things is called kinetic energy. Kinetic energy is just, we're not going to get into it too depth. Just remember, it's just the energy that's needed for things to move across the membrane. So sometimes all that's needed is that kinetic energy. When that happens, that's what we call diffusion. Okay, now what diffusion is just moving things from a high concentration to a low concentration. And all that we need is kinetic energy for that. Now there's two types of diffusion. We have what's called simple or also passive diffusion. And this is essentially when all that's needed is nothing. All that we need is this kinetic energy. So we're going to put red. That's going to be our cell membrane here. And we're going to keep our brown. Our brown is just going to be all of our solutes on the outside in our ECF. This is our ICF, so inside the cell. Our ECF, that's where the concentration of these solutes is very, very high. And then our ECF, that's where the concentration of these solutes is lower. Excuse me. So for passive diffusion, all that's going to happen is just our solutes from our high concentration are just going to move down into low concentration. And that's it. That's all that happens. But not every molecule, not every solute is able to do this. So this would be things for like, say like just smaller molecules. So mostly what's going to be doing this simple passive diffusion is going to be our oxygen and our carbon dioxide. So it's going to be able to do that. Okay, but not everything is able to do that. So let's see, let's erase all this. And keep our cell membrane though. Okay, so, let's backspace. Going back to simple diffusion. There's a certain equation that we can use to determine how fast our solutes are diffusing across the membrane. Okay, our equation is called Fick's law. Is going to be J equals negative D times A times delta C divided by X. Make sure I got that right. Yep, perfect. Okay, so our J, that's just the net rate of diffusion. So that's what we're trying to find, is just how much something is diffusing. Our D, that is going to be our coefficient, or our diffusion coefficient. Our A, that's going to be surface area of our membrane. Then our C, that's going to be, or I guess our delta C, that's going to be our difference in concentrations. And then our X, that's going to be the thickness of the membrane. Sorry, got a little sloppy there. So essentially we can take this equation and determine how fast our solutes are going to be able to diffuse and how these certain variables are able to affect that diffusion rate. So if we increased our diffusion coefficient, that's going to increase our rate of diffusion. If we increased our area of the membrane, also going to increase it. If we increase our delta C, that's also going to increase our net rate. If we increased our delta X, though, that is going to decrease our net rate of diffusion. Okay, so essentially if we were to graph out, let me see if I can, yeah, okay. If we were to graph out, so this is going to be our rate of diffusion time. For simple diffusion, essentially what we would see is just as we, actually no, that is not time, my bad. Concentration. As we increase our concentration, our rate is going to increase. So the higher the concentration means the higher the rate of diffusion, okay? Okay, but say you're not oxygen, say you're not CO2, and you can't diffuse via simple diffusion or passive diffusion, you just need a little extra help. So we call this facilitated diffusion. Okay, and for facilitated diffusion, essentially you just need a little bit of extra help. So what you need is proteins. So some sort of protein in our cell membrane to help that diffusion occur. Okay, so let's do a pretty big cell membrane because we're going to draw several different proteins here. All their different types. Okay. So let's start with, go here. Put our little protein here. Okay, so say we have, right, so for this whole thing, right, because it's diffusion, we want to move high to low concentration. So we're just going to put a bunch of these solutes on this side of the membrane and just a few on this other side. Remember, this is our extracellular fluid, and this is our intracellular fluid. Okay, we want to move these solutes into the cell. Okay, so say this is our protein, right? And it's almost like a gate. It's locking them down so nothing can pass through there right now. So we need to open this gate first. So let's say we have some sort of environmental factors. Say we have, let's say touch. So someone or something touches the cell. So we apply some, that's not how you spell touch. Touch, right, to that protein. And what that's going to do is, because of that environmental condition, it's going to push on the cell membrane and it's going to open up those gates, okay? So now our gate is now opened and these solutes can start to move out. So we would call a protein like that is called a mechanically gated. Okay, so now let's move on, go over here. Our little protein here. I'll put something just like that, okay? Now, so this, it looks like it's open, but there's actually some sort of a gate, some sort of a blockade there that keeps our solutes from moving through. Now, this protein, it's going to open via change in voltage. So say we're at a resting potential of negative 70 millivolts. Okay, but say that changes somehow, could be just some sort of change in ion concentration, action potential, something like that, and that's going to change, let's say, negative 30 millivolts. So because of this change in voltage, this protein, or this gate, is going to swing out. It's going to open up our gate and allow our solutes to diffuse through the membrane. So this is what we would call voltage gated. Okay? Let's go to our last one here. Last one we'll go over for this. So we'll put our protein here and our little gate. And I wish I had another colored marker here, but we don't, so we're just going to have to work with it. Okay, so this one, on our protein we'd have right here is just some sort of chemical receptor. And what's going to happen is we're going to have a ligand come through here. So this is our ligand, and a ligand is just some sort of chemical, okay? Our ligand is going to come in and it's going to bind to that receptor, and that's going to open up our gate here. So let's kind of erase this a little bit. So now our gate is opened, and here we'll have our receptor with our ligand bound to it. So because that ligand or that chemical bound to the receptor, now our solutes are able to diffuse through the membrane. Okay. Let's see here. There's other things that we have that would also let's see here. Kind of redraw this here. We could also have just what's called leak channels. Put something like that. It's kind of like a little tube thing. Let's have leak channels. Our common leak channel is going to be our potassium ion leak channel. Okay, and these leak channels, usually potassium leak channels, that's going to open via some sort of action potential is going to hit it and open up that leak channel. But there's our leak channels that would also can open up and diffuse solutes across. Potassium is actually higher on the inside of the cell, so it diffuses out through our leak channels. There's also what's called carrier proteins. Let's see if I can draw a good carrier protein here. Let's see if we did. Let's do something like not like that. Backspace. Okay, so essentially what that would do is a very, very specific protein is going to come in. It's going to bind to that. Now this is very specific. Most of these, if not all of them, are very specific for the type of ions, solutes, whatever that's coming through. We can't just open up a potassium leak channel and sodium, chloride, all those are going to come in. Usually these are very specific for the type of things that it brings in or out of the cell. So very specific, we'll say this is a protein. Very specific protein is going to come bind to this. And what that's going to do is it's going to cause our carrier protein to change shape. So it comes in here, and now it's going to kind of reverse itself. So now it's going to do something like this. So now it's open on this side, and then it's able to go through. So it'll enter that side, bind, and then it's able to change the shape of that protein so it spits it out on this inside. Okay, now, let's erase all this. With the facilitated diffusion, because we need proteins to cause that to happen, let's draw our membrane back. So let's draw a little protein here too. Won't be super detailed. We'll just put some sort of protein there. All our high solutes over here, low solutes over here. Okay. we're not going to see the same rate of diffusion, at least as far as a graph goes, with facilitated diffusion as you would with simple diffusion. What we would see instead is just like, so we have our concentration on our x-axis, and our rate is our y. Instead, what we'd see is our concentration would grow and grow and grow and grow. Our rate would start to increase, and then we would have a plateau here. And at this plateau, so at this point, this is where it gets saturated. So what saturation is, it's essentially like if we had this door right here, and we just sent everybody all out the door at once, the whole class. So everybody would kind of be stuck at the door as they kind of started to trickle out. So what's happening is there's too many proteins right here. It's so concentrated up here, it's not able to get all of them through very quickly. So it has to kind of just quickly, very slowly kind of poop them out one by one. So we'd see this plateau where it just becomes too much, too saturated to where the rate's not going up and it's just going to plateau. We've hit kind of our maximum rate of diffusion there. Okay, I believe that's all we have for diffusion as far as what happens there. So now we're going to talk about transports. Let me get all this erased here. Okay, so we're going to talk about what's called active transport. So with diffusion, what happened is we wanted to move solids from a high concentration to a low concentration. But this is if we want to move things from a low concentration to a high concentration. So against its gradient. Okay. Normally solutes, they want to move with that high to low gradient. It's almost like if you're at the top of a mountain, you want to get to the bottom of the mountain. So you're high, you want to get to the low. Water, say, is going to naturally flow high to low. It's never going to go low to high. So what's going to happen if we want to go from low to high? Low to high concentration. Okay. What we would need is more than kinetic energy, because right, our kinetic energy is just what moved the water from high to low. We're going to need a little more than that to move from low to high. Okay. So usually with active transport, well, not usually, always with active transport, we're going to need some sort of energy source. And usually that energy source is ATP, right? So ATP, that's going to be what's used in our primary active transport, is ATP. Okay, that's where we directly use ATP, is in our primary active transport. So what's happening there, let's get our cell membrane again. This is some sort of, we'll call it a pump. So I have our pump here. Let's use a specific ion. Let's use sodium, okay? So sodium is going to be high outside. We'll just do this. So we're going to write a big sodium, indicating that you have a higher concentration outside the cell. And then just a little sodium inside the cell, okay? But we want to move our little cells outside the cell in order to maintain a high concentration on the outside cell. But obviously that's not how it naturally wants to flow. So what we need in order for this to happen is we're going to need ATP to come in. And with that ATP, with the energy from that, we're able to move our sodium from its low concentration out to its high concentration. Okay, and that is primary active transport. Okay, but let's say we're going to do, let's see here, see how we want to do this. Okay, so now we're going to talk about secondary active transport. Okay, so we have our cell membrane here again. Now let's draw our little pump here. Okay. So with secondary active transport, what we're using is we're using the gradient of another material, another ion solute, and just the movement of that gradient is from the energy from that is what's going to power the other gradient to move our low to high concentration. So let's put a note here. So we're going to have one with the gradient and one without. Okay, so let's do, just for kicks and giggles, we'll put chloride is really high on the outside, and we have a little bit of chloride here. We'll do potassium really high inside, potassium really small outside. Okay. This isn't actually, as far as I know, this is an actual process. We're just going to use this as an example. So don't quote me on this. Don't go trying to teach about chloride potassium pumps, because as far as I know, those don't exist. Just an example, okay? So what we're going to want is first we need one gradient. Let's say our end goal is we want to move some potassium inside the cell, okay? That's our end goal. So what we're going to do that is we're going to need a high to low concentration gradient, okay? So we're going to need our chloride is going to go from its high concentration to its low concentration. And the energy produced from that gradient movement is going to be enough energy that we can move our potassium outside the cell in its low concentration down to its high concentration. Okay, so that's the gist of secondary active transport. Now there's two types. You can see that our gradients here are both going in the same direction. If it's going in the same direction, that's called symport, secondary active transport. Okay, both our gradients are going in the same direction, yet we have one gradient that's going with its high to low concentration gradient, which powers our other gradient to go from low to high concentration. Okay. Now let's see. There's two types. There's symport. There's also called antiport. So let's see how we're going to draw that out here. Okay, so we're going to use sodium high there, and then we're going to use, actually no, let's see, yeah, no, so let me think this through really quick. Okay, so we're going to use this as an example, okay? So we have sodium and chloride, both high on one side of our cell membrane and both low on the other side of the membrane, okay? Our end goal is you want sodium on the outside of the cell, okay, to maintain this gradient. So what we're going to do is we're going to have our chloride is going to go through, down its gradient, its high-low gradient, into the cell. And that energy is going to be able to power our sodium from the inside of the cell to its high concentration on the outside of the cell. Okay. Same thing, we're going to use our energy from our high to low concentration gradient to power our low to high concentration gradient. And with that energy, we're able to move our sodium to the outside cell. But as you can see, our gradients are going in the opposite directions. Our chloride is going into the cell and our sodium is going out of the cell. So if they're going opposite directions, that's going to be what's called antiport. Okay, and that is essentially all we need to know about membrane transport as far as diffusion, active transport, and whatnot. So let me pause and then we'll move on to our next topic here. All right, here we are for our last part of our essay video. If you're the grader grading this right now, thanks for bearing with me. Sorry, this is a little bit longer than I anticipated. but I'll try to make this one short and sweet while also hitting on all the topics. So we're going to talk about osmolarity. What osmolarity is it's going to be moles of particles per liter of solution, which sounds very, very similar to molarity, but the difference between osmolarity and molarity is osmolarity is moles of particles per liter of solution, while molarity is going to be moles of molecules per liter of solution. You might be asking, well, why is that? How is that any different? Well, let's say we have a molecule such as sodium chloride. Okay, so say our molarity is going to be, I don't know if this is right, but we're going to have 1 mole of sodium chloride per 1 liter of solution. Okay, but what happens is when sodium chloride enters the solution, it dissociates and separates into 2 different ions. So we'd have our sodium ion and our chloride ion. Okay, so we have 2 different particles now. So now I went from the molarity of 1 to 1. So now our osmolarity would say be 2 particles per 1 liter. Okay. I think with sodium chloride it's actually something like 1.8, but we're not going to worry about that. Okay, so that would be the difference between osmolarity and molarity. So osmolarity is essentially the number of particles in our solution that we want. Okay, so for osmolarity in our blood, the normal, or I guess not necessarily our blood, but inside of the cell, our normal osmolarity is going to be 300 milliosmoles. Okay, so that one thing with osmolarity is it has a unit. Okay, has a unit. Okay, now if we were explaining, I guess the difference in osmolarity between, say, a solution and a cell. Let's say we have our beaker of solution. We're going to say this is 0.9% sodium chloride. Okay. Now 0.9% sodium chloride also happens to have an osmolarity of about 300 milliosmoles. Okay. So we have 300 milliosmoles in our solution, and then we have our cell also 300 milliosmoles. So this would be what's called a isoosmotic solution, or isoosmotic. Okay, our cell is isoosmotic compared to the solution, and the solution is isoosmotic compared to the cell. Okay, now let's see. We didn't do 0.9 sodium chloride. Say we did. Say let's do. We did 0.45 sodium chloride. Okay, so that just dropped it. So now we went from 300 milliosmoles to now we're at 150 milliosmoles compared to our cell, which is 300 milliosmoles. Okay, so what would be here is now our cell, because it has a higher osmolarity, our cell is going to be hyperosmotic compared to our solution. And then our solution, because it has less osmolarity than the cell, is going to be hypoosmotic compared to the cell. Okay? So that is our osmolarity. And the process of osmosis, so we've heard about osmosis in, say, like Bio 180. Osmosis is essentially the process of moving water, it's not just solutes, but water across a permeable membrane, okay? And we'll get into that as we explain tonicity here. So remember, osmolarity, that's always going to have a unit. Tonicity, though, is going to be unitless. So tonicity does not have a unit. It's unitless, okay? And tonicity is essentially the effect of our osmolarity, okay? So that's going to be how our cell changes in volume, okay? That's going to be the tonicity. So let's run through a few things. One thing to note is 0.9% sodium chloride, 5% dextrose, which is just glucose, by the way, and urea, lactate, and let's go, yeah, let's just work with those three for now. Okay, those are all right around 300 milliosmoles. Okay, so now let's explain how these could affect our tonicity. Okay, let's do a different color. I don't know how well that's showing up in our video now that I realize it, but it should be okay. So let's do, which one? Let's do 5% dextrose. Okay, so we have our beaker, right? So our beaker, this is 5% dextrose, which is just glucose, okay? And this has 300 milliosmoles, and then our cell also has 300 milliosmoles, okay? So our solution to cell comparison, that is going to be isosmotic. But we want to see what the effect would be if we took this cell and put it in our solution, okay? So now let's move here, okay? Our cell here, 300, and our solution is 300, okay? But one thing you have to know about dextrose and glucose is what's called a penetrating solute. What penetrating means is that it is able to penetrate through our membrane, okay? So what's going to happen is we have our dextrose or glucose, we put our cell in that solution, and osmosis is going to occur. So all this water and all those is going to move through our cell, okay? So now all of our dextrose particles, because they're penetrating, is going to move through that, okay? So we just went from, so I guess our solution went from 300 to 0. There's nothing else in its solution. No glucose in our solution anymore. But the interesting thing with glucose is our glucose is going to enter the cell, and that's going to be metabolized. So our cell's going to hurry and use that glucose. So then, rather than it jumping to 600, it's just going to stay the same. It'll be at 600 for a little bit, gets metabolized, and we stay at 300. But now we can see that our osmolarities are different, okay? So now osmosis is going to occur. I guess osmosis occurred I guess it didn't really occur when the glucose was moving through, because osmosis is just water. Anyway, so let's go. So now osmosis is going to occur where all this water, because it's lower here and higher inside, what's going to happen is our water, it likes to follow our solutes. So because we have more solutes inside the cell, osmosis is going to occur. Our water is going to move into the cell, and it's going to burst. It's going to swell up, and it's going to burst. But again, because our solution is lower than our cell, this is what's called hypotonic. Okay? So we did have an isoosmotic solution originally. Originally, 5% dextrose is isoosmotic. But when we put our cell in it, it becomes hypotonic because of the effect that it has on our cell volume. Essentially, like everything happens, it moves into the cell, gets metabolized, becomes hypotonic, and now it's going to cause our cell to grow and to burst, okay? Let's do another example, and then we'll move on, and I think that is all we have to cover. So now let's say we have a solution of 0.9% sodium chloride, not TL, with a 5% dextrose. Okay, so we have our beaker here of those solutions and our cell. 300. Okay, so we have 300 plus 300, so now we're going to have a solution with 600 milliosmoles. Okay, so now this solution is going to be hyperosmotic compared to our cell. Okay, but now let's go into our tonicity. So now we have our solution here, and our cell, 300, this is going to be 600. We're going to have all of our dextrose. Then we're going to have all of our sodium chloride. Okay. Remember, dextrose or glucose is a penetrating solute. So it's going to go into the cell, and when it goes into this cell, what's going to happen is it's going to get metabolized. So essentially, we're just going to erase all of our dextrose or glucose. Okay. And that drops it to 300. Okay, but what about with our sodium chloride? Sodium chloride is non-penetrating, so it's not going to go through our cell membrane. Okay, non-penetrating. So then this is just going to stay 300 milliosmoles. Our cell is also going to stay 300 milliosmoles because remember it metabolized our glucose. So now this is going to be a isotonic solution. Okay. That is essentially osmolarity and tonicity and what we need to remember for that. Thanks for watching. Have a good day.